Hello. Today we are going to be taking a look at a physics problem. It's going to be related to the kinematics unit, and we're going to be using some of our big five equations in order to solve this one-dimensional kinematics problem. So I'll read through the problem and then we'll solve through the questions together. So a police car stopped at a set of lights has a speeder pass it at 100 kilometers per hour. If the police car can accelerate at 3.6 meters per second, solve the following. How long it takes to catch the speeder, so that'll be our time. How far would the police have to go before it catches the speeder, so that'll be our displacement in the horizontal or x dimension. And then finally, what is its speed when it catches the speeder, okay? So that'll be our final speed. And like I said, we are dealing with a one-dimensional type of problem here, so I will just draw my compass on the side to note my positive and negative directions. So I'll say that forwards will be positive and backwards will be negative. And finally, I'm also going to draw a diagram here just so we can visualize what we're working with before we solve our questions. So let's say this is our cop. They're originally at rest. And right, so therefore we're going to have our initial velocity of 0. And then we know we're going to be accelerating at 3.6 meters per second squared. Forwards are in the positive direction as soon as the speeder passes us. So we're at rest, and then there's going to be some speeder, right? Speeder's going to come by at some velocity. We'll classify this as some initial velocity of 100 kilometers per hour. And they're going to be speeding right by the cop. And then right at that instant, right, where it passes the cop is going to start accelerating at 3.6 meters per second squared until eventually the cop catches up to the speeder, okay? So it's important that we note that our initial position, right, our initial state is going to be here, right? Right at this instant, this is where we're evaluating our initial state, and then our final state is going to be where the cop eventually catches up to the speeder. We can also assume, since we're not given any other information about the speeder, that we can say that the acceleration of our speeder, right, is going to be 0, right? So it'll be maintaining that 100 kilometers per hour speed. And finally, one last thing before we solve our questions is that I'm given an acceleration in terms of 3.6 meters per second squared, but I have a velocity here of 100 kilometers per hour. So it's important that when solving any physics problem, I ensure that I have the same type of units. Okay, so I want to make sure that, right, these will be the same. I'm going to convert this kilometers per hour into meters per second. And to do that, I'm going to use my ratio of 3.6. So that'll be, in this case, I'm going to divide my 100 kilometers per hour by 3.6. And when I calculate that, I'm going to get about 27.78 meters per second. Okay? For my VI, and again, that'll also be in the forwards direction. Okay, now that we've got this set up, we can go ahead and solve the first problem. Okay, so how long it takes to catch the speeder. So I got to somehow figure out how and at what time the cop catches up to the speeder. Now, this is going to be very similar to our math unit where we have some type of point of intersection that we need to solve for. So if I'm given two equations, right, I'm going to need to solve kind of where those lines or where the line intersects with some type of parabola. So it'll be the same concept here. Since I have two objects that I'm dealing with in my physics problem, I can assume that I should first go ahead and set up two different equations, and that's exactly what I'm going to do. So if I'm evaluating my COP, so let's say for my COP, right, I'm going to use this equation here, delta D equals my initial velocity times my time plus 1/2 times my acceleration times time squared. And I know that for my COP, my initial velocity is 0, right? So that'll just be 0 times time, which this whole term will just go to 0. So I would be left with delta D equals, right, this has gone to 0, so just 1/2 times my acceleration, which is positive 3.6, times my time squared. Or, finally, delta D equals 1.8 delta T squared. Next, I'll do the same thing, but set up my equation for my speeder. So here, I'll use the same equation, delta D equals VI initial velocity times our time plus 1/2 times our acceleration times time squared. With our speeder, we don't have an acceleration, right? So our acceleration is 0, so 0 times 1/2 times our time will make the whole term go to 0. So I'll just be left with delta D equals my initial velocity, which is positive 27.78 times our time. Okay? Now I've got two equations, and I've got two unknowns. So what I can do here, right, is solve these two systems of equations. And I can do that by using substitution. I can set, right, I can just sub in this 1.8 delta T squared into here, right? So if I classify this as equation 1 and equation 2, I can make a note here and say sub 1 into 2. And the reason why I can do that is because I know that eventually their distances are going to be equivalent to each other, right? Eventually the COP is going to accelerate until it reaches the speeder, and at that time they're going to have the same distance, right? They're going to have the same distance, and therefore I can solve for that time in which they both meet each other. Therefore, how long it takes to catch the speeder and solve our part A. So I'm just going to plug 1.8 times t squared into here. So, right, I'll have 1.8 times my time squared equals 27.78 delta t. I'll move this over and set the whole equation equal to 0. So I'll have 1.8 delta t squared minus, moved it over so it'll become minus 27.78 delta t equals 0. And now what I can do is I can factor out a t. So I'll have delta t times 1.8 delta t minus 27.78 equals 0. So now what I can do to solve for my time is set my two terms equal to 0, right? So this term, it'll just be time equals 0. And then for this term, let me bring it around over here. I'll have 1.8 t minus 27.78 equals 0. I'll move the 27.78 over. I'll have 1.8 delta t equals 27.78, and then divide both sides by 1.8, which will give me a time of approximately 15.43 seconds. Really cool thing here, right? Because we know that initially at time 0, based on how we set up our question, they're going to be, right? They're going to have the same distance. This is what this is telling us. This what we just solved for here. We solved for the 2 points in which the cop and the speeder intersect with each other. And they, like we stated, they intersect at the beginning, right? And then finally, after some 15.43 seconds, their distances are going to essentially intersect again. So pretty cool concept there. And to conclude the question, we can say, therefore, it takes the cop 15.43 seconds to catch up to the speeder. Alright, next I want to find how far would the police have to go before it catches the speeder. So we can easily just sub in our time into one of our equations, right, from part A, or I can just sub it into any of my other kinematics equations and essentially solve for the distance. So if I'm to do it from scratch, I'm just going to I can take that same formula again, right? Delta D equals VI times delta T plus 1/2 times our acceleration times our time squared. For our cop, right, this initial velocity, like we stated, is 0, so this whole term will go to 0. 0 times that time, right? Take the whole term to 0 times, or then it'll be equal to delta D equals 1/2 times our acceleration, which we know is positive 3.6 times our time, 15.43 squared. And then when I put that in my calculator, I'm going to get a distance of 428.6 meters. Okay, so the distance the cop had to travel in order to catch up to the speeder, right, was 428.6 meters. Finally, we now want to find what is the speed of our cop once it catches up to our speeder. So the cop's going to be accelerating until that point in which it catches up to the speeder. We want to find at that instant what is our cop's velocity. So I'm going to classify that as the cop's final velocity. And I have the cop's initial velocity, I've got its acceleration, and I could also use either the time or distance to help us solve that. So what I'm going to do is I'm going to use another one of our big 5 kinematics equations. I'm going to use this one, final velocity equals initial velocity plus our acceleration times our time. Okay? Like we said before, our initial velocity is 0, so then I'll just be left with our initial velocity equals our acceleration, which is 3.6, positive 3.6 times our time, which is 15.43 seconds. And when I put that in my calculator, I'm going to get a final velocity of 55.5 meters per second. And if I wanted to convert this back into kilometers per hour, I can just now multiply this by 3.6, and then that'll give me a final velocity of, rounded up, basically 200 kilometers per hour. So pretty fast. A pretty good multi-step 2-object kinematics problem here. Hope it helped. If you guys got any questions or comments, let me know, and thanks for watching.